Okay, so this is the week 6R code. First thing we're going to do, just set to the right directory with all our files in it. Then kind of put the library for loading Excel files into memory. Now load in the autos Excel file. Now, if we kind of quickly look, this was the example we did with the Japanese cars in Japan and the Japanese cars in Japanese cars in the US and the Japanese cars in Japan. And let's just have a look what we get with our autos data. So we have basically the columns we want. Remember we had this in two different formats for SPSS. We're just going to get the US and the Japan. We're just going to extract it. We're only using the first 50. We only have the first 50 items here because in the third and fourth column we have like 100 items and then the two groups. So we're just going to get these two pieces of information into two vectors called USA and Japan. We calculate the lengths, and this is really equivalent to doing it by hand. So we calculate the standard error. Remember this was, let's just have a look down here. This is this at the bottom, the square root of S1 squared over N1 plus S2 squared over N2. We calculate the differences in means. And then we're going to do this first as a confidence interval. And again, we use the Q norm to get the 1 minus alpha over 2. And we set alpha to be 0.05 at the top, so this gives us 1.96. Multiply by the standard error we've already calculated, gives us our margin of error. And then we just add it and subtract it. And here's our confidence interval. There we go, the same result we got in class. Now let's do the actual hypothesis test. So the Z is the difference in the mean divided by the standard error. Now when we did it as a test, we actually did it as a one-tail test. So we were actually trying to find if US minus Japan is less than 0, i.e. are the manufacturers selling cheaper in the US than in Japan? So we're just really looking at the left here. So Q norm minus 1.65 for alpha equals 0.05. So we basically reject if Z is less than minus 1.645. And all we're doing here is we're just printing out the results of the test. So we can also calculate the p-value, which using the p-norm function. And then sprintf, this is just a fancy way of formatting. So we have Z equals the value of Z, and 4f is just the kind of basically the formatting code. So I'll show you how that works. So it just tells us we've got 4 decimal places on each of these. So we're going to do Z equals minus 1.618. The critical value is minus 1.645. So we fail to reject and we get the p-value of 0.0528. Now, remember we talked about how statisticians really don't like this estimating the population standard deviation as a sample standard deviation. So R, designed by statisticians, doesn't actually implement the two-sample z-test. But there is a library called BSDA that does. And it actually, basically, there's a function called z-test, where again, we pass our two pieces of data. Okay, so we have the alternative hypothesis is a less than. We can have less, greater, or two-sided. We don't know the population value, so we have to estimate it from the sample. So we just pass, using the SD function, the two different sample standard deviations. And let's do the z-test. I'm not quite sure what's happening with the confidence interval here. I guess that it's, it's set to a certain value. But anyway, we're interested in the two-sample z-test. And we have the z values we calculated by hand, and we have exactly the same p-value. So this is a way, I did it by hand, but this is a way of just doing a two-sample z-test with a third-party library. Okay, so let's move on to the success. This is kind of very, very simple. So again, this is the management successes. And let's just remember we did this in SPSS. So let's just look at our SPSS results. SPSS, we basically did the Levene test. And because we failed to reject we said the variances are equal, so we did the student t-test rather than the Welsh's t-test. So we're going to do the kind of the same here with our success data. So let's just kind of load in success. And let's just see what we have as the group. So we basically have, we're making the group a factor. Now we're using a slightly different format here. What we're doing is we're doing almost like a regression format. So we're passing the data and we're just saying the dependent variable is success, and then we're going to do it by group. So this is just kind of you know, one way of doing the t-test. So let's just do it like this. And here we go. We recognize these figures from the slides. So it's got an incredibly low p-value. We've got a t of 4.9675. This is the other way of doing the t-test. And we get exactly the same result. So all this is doing is, if you look at the success data again, we've got 4 columns. We've got basically success and group. This is every success value with a column to say, are we in group 1 or 2? And we have the separate group values. So we can do it one way where we say, okay, our dependent variable is success, and we're going to do a test with 2 groups, where groups is like the independent variable, or we just pass it the 2 groups, we get the same answer. Okay, so we are going to run Levene's test. And for this, we require the car library. And Levene's test is going to work basically success to group, and we pass the data success. And again, the Levene's test basically says fail to reject. So let's just kind of compare it with this is a significance of 0.218 and we're 0.229. So it must be a slightly different variant of Levene's test. Maybe it's not a test that's quite this, there's maybe multiple variants of it, but we have very similar results. So we failed to reject. So when we do the t-test, we can use var.equal. And var.equal is actually the default. So we get the pretty much, I think we'll actually put I always like to do things explicitly if I can, rather than relying on defaults, which could change. We do the t-test as before. Okay, so it works very, very similarly to SPSS. Okay, so now let's work through the last example we did, which was the telephone example. And here, I won't kind of bore you with all the calculations because this is the ones we've just done in class. But remember, we had basically, let's just go to our data. We have N1, X1, N2, X2. It's our 2, telephone surveys, how many people purchased. And from that, we can calculate the estimates of P hat 1 and P hat 2 and Q hat 1 and Q hat 2. So all this code does is basically do that. So we've got the N's and the X's, then we calculate the P hats and the Q hats. We find the difference between these. We find the standard error, which was the square root of P hat 1 times Q hat 1 over N1 plus P hat 2 times Q hat 2 all over N2. So just these calculations here. We don't want to look at Google. And calculate the standard error and calculate the alpha. So the first thing we're going to do is the confidence interval. So basically, again, we use the alpha equals 0.05. So use a Q norm function to get 1.96 times the standard error. That's our margin of error. And the confidence interval is just the difference between the 2 p hats. So 0.0042 minus 0.0026 plus or minus the margin of error. And there we go, we get exactly the same results in the class. We don't quite go through 0. So we're just, if we use the same kind of denominator, we're just about significant. Okay, so now do the hypothesis test as before. Now we're going to use the combined test where we have p hat. So let's just do this. So we're going to do this test where we calculate p hat and q hat, and then we're going to do multiply by 1 over n1 plus 1 over n2. So we calculate p hat and we calculate q hat. So p hat, for example, was 0.033 as we calculated in class. And then we calculate that standard error I just showed you, p hat times q hat times 1 over n1 plus 1 over n2. And from that, we do basically the difference divided by the standard error. We get the z. And we get 2.25, which again is mildly significant. We're doing a two-tailed test, so we're looking at absolute value of z is greater than z. Again, R like Excel goes left to right, so this is 0.975, which has given us a value of 1.96. So do we reject? Yes, because our absolute value of z is greater than our value. And again, we calculate the p-value. And again, because if we're to the left, we use p-norm z. If we're to the right, we use 1 minus p-norm z, as r is always going left to right. So we use basically the smallest value, we multiply it by 2. So let's just kind of do the final thing. And here we go. So z equals 2.25, critical 1.96, reject equals true. And yeah, the p-value is 0.02, which is significantly less than 0.05. Interestingly, R actually has an inbuilt, like SPSS, as an inbuilt proportion test. And what we do is we send it a little mini vector with both my x1 and x2, and another mini vector with my n1 and n2. We don't basically send any kind of difference in proportion. Well, because this is a two-sample test, we don't actually have a hypothesized value. We're just saying, is there a difference here? We're going to do two-sided. Now, correct equals false. It does it a little bit like the first SPSS I showed you. It assumes the chi-squared test calculates the chi-squared, and then does the square root of that. Now, chi-squared we'll talk about has what's called a continuity correction for small tables, and basically we don't want to use this. We want the standard test. So we can do the proportion test, and you can see we got the chi. So it gives us the chi-squared. If we did a square root of this, we'd get our z value from before, but we get exactly the same p-value. So we could say to reject, and we can also, it actually gives us the same confidence interval that we had before. So we actually can do the two-sample proportion test, which I thought was kind of quite interesting. Okay, so that's all the tests for this week.